Okay, in this video we're going to be looking at the definition of binomial distribution. Okay, for a situation to be modelled with a binomial distribution, it must satisfy each of four conditions. So this is the definition of what a binomial distribution is. So there must be a fixed number of trials, there must be exactly two outcomes, there must be a fixed probability of success, and the trials must be independent. So when we are deciding whether we can apply a binomial distribution to a certain scenario, we should be thinking about those four things. And thinking in our mind, okay, well, does this have a fixed number of trials, yes or no? Does this have only two outcomes? The bi in binomial is that's where the two outcomes comes from. Are these probabilities fixed each time, and are they independent? And each time we are thinking yes or no, it applies. If all four of the criteria are set, then we can use binomial distribution to model this scenario. Okay, so what I'm going to do now is I'm going to just look at some scenarios by way of example, and I'm going to consider each of those conditions, and I'm going to decide whether it is met or not met within this scenario, or if it's a little bit unclear. I think, as you found with statistics, there's not always a absolutely rock solid certain answer. There's a little bit of nuance involved. So I'm going to do the first one. I'm going to ask you to pause the video and then think about the others, and then I'll go through the others. Okay, so let's start. So I've got a pair of unbiased dice are thrown 100 times. I want to model the number of times a 7 is thrown. Okay, so the first thing is I am throwing some dice 100 times. So I've got a fixed number of trials. The number of times I'm doing this is 100. So that's set. Exactly two outcomes. Now I'm looking to model the number of times a 7 is thrown. So what I'm interested in is whether a 7 is thrown or whether a 7 is not thrown. So those are the only two things that can happen, either a 7 or not a 7. So that is a Y. Okay, fixed probability. So each time I throw these dice, the probability of getting a 7 is the same each time. And I think it works out as 1 out of 6, doesn't it? The probability of getting a 7 from two dice. So that is set. So that again is true. Okay, the trials are independent. So what this means is that if trials are independent, it means that what happens on one trial does not affect the probability on the next trial. So if I throw a 7, then the probability the next time is unaffected. Okay, so they are independent. These two things are independent of each other. So that again is true. So what we have concluded here is that the binomial distribution is an appropriate model to make predictions on this. Okay, so we can say yes for that. Okay, so I want you to pause the video now. I want you to have a little think about these. Don't worry if you're not sure, and then I'll go through them. Okay, so press pause now. Okay, right, so let's have a work through these. Hopefully you've had a little think about them. A random sample of 20 bolts is checked for defects. 1% of the bolts have defects. Model the number of bolts with defects that will be found. Okay, so fixed number of trials. So we've got 20 bolts, so I'm testing 20 bolts 20 times. So that is it. So that's a yes. 1% of the bolts have defects. Now, one of the things that's important here is that let me take this one step at a time. So exactly two outcomes. So when we test a bolt will either have a defect or not have a defect. So again, that is two outcomes. Okay. I'm just going to look at this independence one before I go to the fixed probability. So let's look carefully at the wording of this. It says a random sample of 20 bolts, doesn't it? So it's not 20 bolts out of one batch. So it could be that a factory is making bolts, and I would suggest that if a bolt on a batch has a defect, then the probability of other bolts in that batch having a defect would be higher, because there might be something wrong with that run. So these trials are would not necessarily be independent. But the fact that we have stipulated that we're going to take a random sample of 20 bolts, so they can come from any batch and any different machines or that, but it is a random sample, that is going to give us the confidence to say that those trials are independent. Okay, and because they're independent, we've got a fixed probability, so it's 1% is our probability every single time, and it's not going to change. So once again, we can confirm that is suitable for binomial distribution. Okay, the next one. On average, 6 telephone calls are received by call centre every 5 minutes. Model the number of telephone calls that will be received in an hour. This is completely different, isn't it? This is a totally different scenario. We're not testing a fixed number of things with a probability. It's finding out how many times something is going to happen in a period, isn't it? This is just it's just not right, is it? It's just not a binomial distribution. So let's say no. And just for interest, this is actually maybe appropriate for what we call a Poisson distribution, which is not part of the maths course, so not something you need to worry about for the moment. But if you want to have a look at it, by all means do so. Okay, right, next one. So when Andy plays tennis with Tim, on average 1 in 8 of his serves is an ace. How many aces will Andy serve in the next 30 serves against Tim? So fixed number of trials, yeah, we're testing 30 trials, so that's fine. Exactly 2 outcomes, so we want to know how many aces he's served, so he'll either serve an ace or not serve an ace. So again, exactly 2 outcomes. Okay, so right, I'm going to go here again now. I'm just going to go to the independence thing. Now, the wording of this question says that on average, 1 in 8 of his serves is an ace. So presumably that's over a match or over his career or over a season. I'm not sure how that exactly is measured. And we are measuring the next 30 serves against Tim. Now, I think it would be reasonable to say that potentially during certain periods of a match, Andy will serve more aces. So it may be that towards the end of a match he's getting tired and his form drops off. It may be in the middle of a match, once he's got warmed up, the number of aces goes up. So I think there is a question mark about whether these trials are independent. So I think depending on how he's he might just hit a rich vein of form. Sometimes when we're playing sport, we just get in the groove, and he just serves lots of aces for a certain period. So depending on which part of the game he's in, I think this probability could change. I think if the question had said we randomly selected 30 serves during the match, how many of them were aces, I think that would have been a different answer. So I am going to say on that one that binomial is not necessarily, the conditions are not necessarily met. I think it's a slightly nuanced one, that, and a slightly slippery one. I think we could apply binomial, but I think there's a danger that it's not going to be as accurate as we'd like it to be. Okay. Next one. 100 Year 11 boys are randomly selected from across the UK and their heights are recorded. We want to use this to model the heights of all the boys in the UK. Okay, so fixed number of trials, so we're testing 100 boys, so that's fine. We're measuring their heights. Okay, So we've got a problem here, haven't we? Because this is not two outcomes. We're measuring a continuous variable, which is their height. This is not binomial. This is measuring a continuous variable. So I don't need to go any further. It's just not binomial. And this, in fact, would be more appropriate for a normal distribution. And that will be something that you'll be covering a little bit later in the course. Okay. Set of traffic lights have three phases. Stop 48% of the time, wait or get ready 4% of the time, and go 48% of the time. Model the number of times you have to stop on the way to college over a period of 2 weeks. Okay, so let's assume that I'm going to college on weekdays. So I'm going over a period of 2 weeks, so that's 10 days. So I've got a fixed number of trials. Yep, I like that. Exactly two outcomes. So I either stop or go. So that's fine. So if I hit these lights and it's either on stop or it's on wait, I will stop my car. I will stop the light. So 52% of the time I will stop. And I think they're different days. We're told that these are the percentage, so those are independent. So each day it is the same percentage of, it's the same probability that we will hit the lights in one of those two conditions. So I think, again, we can confidently say that binomial would be a good model for that. So our conclusion on this is that, yeah, most definitely the first one, most definitely the second one, most definitely the last one, these two definitely not, and a question mark over this one. I think there could be more information required on that, or but possibly not, yeah? And that would be my conclusion on that sheet. Okay, hope that was helpful.